Earth's getting hotter. Anybody who's looked closely at the evidence agrees. Global warming, caused by carbon dioxide and other gases spewed from cars and homes and factories, has heated the planet an average of about 1.5 degrees Fahrenheit over the last 150 years. Polar regions have warmed even more. It's there, near the North and South Poles, that we've started to see the most dramatic effects of a warmer world. The planet's massive polar ice sheets are all melting.
The ice sheets are melting faster than they've ever melted before, but we don't know how long they'll continue to melt for and how much will melt. So we're trying to look to the past to find an analog for that.
One such analog is a warm period about 3 million years ago called the Pliocene. Ice sheets were smaller then and the sea level was higher, but scientists don't know how much smaller or how much higher. Maureen Ramo is looking for ancient beaches and coral reefs left behind when the Earth subsequently cooled, ice sheets grew, and the seas receded. They could help her determine how high the sea level will rise in Earth's warmer future. Fossil deposits of shellfish and corals permanently mark ancient coastlines like indelible bathtub rings. And if ocean basins were rigid like bathtubs and melting ice sheets were like tub spouts, recounting the history of ice sheets and global sea level would be easy. The elevation of a past shoreline above or below present sea level would define how much the sea has gone up or down around the world when water melted from or accumulated in polar ice sheets.
The bathtub model says if I turn the tap on, that is, I melt ice sheets, the bathtub model tells me, as you've seen in your everyday experience, bathtub stays solid and firm and the water level just rises up uniformly. That's the bathtub model of sea level.
Jerry Mitrovica and a small group of upstart geophysicists have discovered that the model is wrong. It has several flaws, he says. First, continents aren't rigid like the sides of tubs.
What actually happens is the Earth is a deformable planet, right? It isn't a static, rigid ball. As you move ice around, and water around for that matter, you cause that ball to deform. Its shape changes.
When you add water to a tub, its walls stay put. And as you see here, the water goes up evenly all around. The situation is very different when an ice sheet melts into the sea. Here, runoff from a melting glacier raises global sea level like a tub's tap. However, right near the glacier, the ground itself rises up as the ice melts and sheds its huge mass. So the increased water level observed here is less than the global change. Mitrovica explains that Earth's continents rest atop crust, a tough husk akin to a grapefruit's peel that wraps around a more pliable layer inside called the mantle. If you pinched a piece of mantle, it would feel rock solid, but thick polar ice sheets press down with millions of billions of tons of force. Compressed under that great mass for many millennia, mantle rock flows like cold molasses and very slowly gives way. During the last ice age, the crust sagged downward by as much as half a mile under the weight of the huge continental-size ice sheets.
It's going to deform downwards because of the height of that ice sheet. And when the ice sheet disappears, it's going to buoy back up.
For more than 2 million years, Earth has alternated between ice ages and briefer warm spells, each cycle lasting many tens of thousands of years. Earth's in one of the warm periods now. It has been since the last ice age ended thousands of years ago, and yet the crust is still adjusting to the most recent retreat of the ice sheets.
For example, over Canada, when the ice sheet grew, you cause this subsidence. When the ice sheet diminished, it all popped back up. In fact, it's still continuing to pop up today, even though the ice sheets were gone from that region even 10,000 years ago.
Imagine this experiment. You press your thumb gently into a grapefruit. When you release your grip, the depressed peel pops back, like in this animation. It takes a second or so with the fruit. It takes thousands of years for the land of continents to pop back after glaciers release Earth from their icy grip. If one of Ramo's 3-million-year-old beaches was buried by an ice sheet during an ice age, it might still be rebounding today. And if it was near, but not under an ice sheet, something else, but equally important, would be happening. Consider again the grapefruit.
You can imagine sort of pressing your thumb down in one place, you're going to get bulges around your thumb to make up for the pushing down in the middle of your thumb.
Geophysicists call the raised region beyond an ice sheet a peripheral bulge. The vast Laurentide ice sheet that covered half of North America in past ice ages pushed up such a bulge across a vast swath of the continent to the south, including nearly all of the present-day U.S. East Coast.
As this went down, that area bulged upwards. As this came up, that area bulged downwards.
Ramo and Mitrovica must correct for these effects before drawing conclusions about past global sea level. They must also correct for another effect, the gravitational attraction ice sheets exert on seawater. We all know that gravity makes what goes up come down and corrals NASA's satellites around the Earth. Mitrovica and others have realized that there is a powerful gravitational attraction pulling ocean water toward the edge of a massive ice sheet. This gravitational tug increases when an ice sheet grows and dwindles when the ice melts.
But you're reducing the gravitational attraction of the ice sheet on the water. And actually, water will migrate away from a melting ice sheet, right? Because of these gravitational effects.
Thus, near a melting ice sheet, two opposing effects influence local sea level. A weakening gravitational attraction lowers the sea near the ice sheet, while at the same time, water flowing into the ocean raises it. To illustrate, Jerry Mitrovica suggests imagining what would happen if the Greenland ice sheet suddenly collapsed into the sea. Globally, the meltwater would raise sea level by an average of about 22 feet, but nearby, in places like Scotland, Norway, and Newfoundland, the disappearance of the ice sheet's gravitational tug would cause sea level to drop.
These are large effects, so that's a highly counterintuitive result, but it's true.
These and other flaws in the bathtub model mean that when Ramo discovers a Pliocene-age fossil beach like this one in Australia, she can't immediately say how much higher the sea was globally when it was created. First, she needs to adjust the field measurements of her beaches with Mitrovica's Ice Age correction factors, the same way a ship's captain steers to the right when a strong current pushes his or her vessel to the left. Every beach Ramo finds needs a unique factor that takes into account how changes in ice sheets over time have vertically shifted the land, changed gravitational attraction of the ice, and even altered the rotation of the Earth. This Pliocene beach is nearly 90 feet above present sea level. So how much higher was the sea then? The researchers say they don't know yet. Mitrovica says his calculations are most accurate when he's used measurements from many places around the world to compute correction factors. He says that until geologists visit more places and give him more numbers, his estimates will be uncertain.
You can't get anywhere unless you broaden the global database of sea level curves that are associated with that time period. Until you do that, I think you're guessing.
In coming years, Ramo plans visits to sites in Asia, Europe, Africa, and North America. She invites other scientific teams to contribute to the growing database of Pliocene beaches that will be needed to confidently unravel Earth's past climate history.